Welcome to another foss-north. I would like to start by thanking our gold sponsors, our silver sponsors, our base sponsors, and our partners from the community.
So next up is Rikke, who will talk about Oberon on RISC-V. So take it away.
Okay. Hi everyone. I'm Rikke Solbjørg. I'm a master's student based in Trondheim, currently at NTNU. And last year I did a project porting the Oberon system to RISC-V. So I'll be talking about how that went today, things we can learn from it, some interesting things it had to tell me about RISC-V, and what sort of things we can learn from this sort of experience. And I'd like to start by telling you a little bit about both Oberon and RISC-V in case you aren't completely sure about either of them. So I'll start with the one I think more people might be very well aware of, which is RISC-V. So a very brief overview. A processor reads your code by fetching instructions from memory. That's fairly basic. And how it decodes those instructions and understands what to do with them is determined by the instruction set architecture, or ISA. So we have a few major ISAs still in play today, and we have many throughout history. And some of the big ones today are x86 and ARM. I'll be using x86 as a quick example because it's fairly emblematic of modern ISAs, in my opinion. So x86 is by now a really old instruction set architecture. It was started in essentially 1978 by Intel with the 8086 processor, and it's been with us ever since then in most Intel chips in laptops and desktops. And instead of doing any major revisions to it or starting anew, which they tried and that didn't succeed, it's instead grown larger and larger with more and more features and more instructions over the years. So by now it's this massive ISA, and if you pick up the manual, it's a phone book. So that makes it really difficult to work with because it's this large. And in addition to that, it's also proprietary. So it has this complicated licensing scheme by now because it's so old. Parts of it are now open, but parts of it are still closed off. So if you want to use something like x86 in, say, education, that's quite difficult to do. You'll have to figure out some licensing agreements if you want to, say, give your students a task to work with it. And yeah, this can be a pretty horrible situation to be stuck in. So as an alternative, some academics at Berkeley got a bit frustrated with this whole issue. So they developed RISC-V as an alternative instruction set architecture. So it's got a couple of nice features I'll briefly mention. It's free, which should be relevant here. It's permissively licensed, and you can essentially do what you want with it. You can write a RISC-V processor and publish it on GitHub for everyone to use and fork and do what they want with. It's also RISC, meaning reduced instruction set computing. So as opposed to x86, which, like I mentioned, grew massive over time with lots and lots of complicated instructions, it's got a small set of basic instructions, and then they're very careful about adding more instructions on top of that to keep it reduced and simple. And the way they do that is by making it modular and extensible. And this will be really important going forward in this port. If you need more features in your target hardware platform, you'll add a couple of extensions to it. So say if you need floating point operations, you would add instructions for that to your hardware as an extension. Whereas if you don't need that, you can target a hardware platform that only has integer instructions and doesn't even have anything like floating point. So that's RISC-V in a nutshell. Next up, the Oberon system. So Oberon is both a programming language and an operating system. So I have attached a screenshot here of what the Oberon system looks like. And it doesn't exactly look like modern operating systems we might be used to today. It actually started in the... Sorry?
We still see the RISC-V slide.
I
wonder if there's some... now
better?
we see the Oberon slide. Yeah, there seems to be a bandwidth issue. We can always fix it afterwards and sort of embed the slide set, but just so that you know that the picture didn't change.
Okay, well, thanks for letting me know. That's weird. All right. Anyway, this is what it looks like, and it was started in the 80s by Wirt and Gutenknecht in ETH Zurich. So I've attached an image of Niklas Wirt here, who you might also know as the designer of Pascal and Modula. So if you haven't used one of his programming languages, you've definitely used something influenced by one of them. And here's a quick image showcasing the original Oberon system from back in the 80s, running on a custom Series 3 workstation. Now, Wirt retired in 1999 and started afterwards getting requests to republish a textbook he wrote about the Oberon system, because it described the entire system all the way from the kernel to the UI, so you could read the textbook and understand all of it. But the problem was he couldn't republish it because the computer didn't exist anymore. It was custom built at ETH Zurich, and even more than that, even if you wanted to run it on a different computer, the processor was a National Semiconductor processor, and that company also doesn't exist anymore. So he decided to pick up the operating system itself again in 2013, and this time around ran it entirely on an FPGA using a processor he himself designed and created. So as a brief aside, an FPGA is basically a little hardware thing you can write your own hardware to in a language like Verilog, and you can just flash it to the FPGA, and it will essentially run your hardware for you. So you can design your own processor and actually run it without having to manufacture it. So briefly, what sort of things sets Oberon apart and makes it interesting for a project like this? Well, like I've mentioned, it's supposed to be simple, so you're supposed to be able to understand all of it, all the software. And with this new processor, that one was also made very simple, so you can also read and understand the hardware. The entire operating system is written in the Oberon language, so that includes the compiler, the bootloader, the UI, and the kernel, and all of it. And like I've also mentioned, it has this custom instruction set architecture. So most things today are meant for general purpose processors with general purpose architectures, but he decided to make one that was custom made only for the Oberon system. So nothing else can ever run on that processor unless you really wanted to. So let's start porting proper and start by basically discovering our target architecture for RISC-V. So
I think you need to enforce the slideshow here again.
That's really strange. All right, I'll try to stop my camera and we'll see if that fixes it.
It did. It's a lot sharper already.
Oh, great. Okay. Well, maybe my internet connection is bad then. Okay. Well, let's find our RISC-V platform. So I'll do that by looking at the processor that Wirt designed. And confusingly, that processor is also running what he calls RISC-V, but with an Arabic numeral. So to try to keep them unambiguous, I'll be calling that Wirt RISC-V to disambiguate it from the open free RISC-V, which we're interested in today. So this is Wirt's RISC-V instruction set architecture, and it's a total of 18 instructions, mostly basic ones, a few floating point instructions, and 3 for interrupts. So I figured we'd need some floating point, and we need to work with some interrupts. But then I started looking through the source code for the entire operating system, and it turns out that floating point numbers are never used in the entire operating system. So there's support for them there, but you can have a fully functional port of the system without ever using floating point arithmetic. It's never necessary. And surprisingly, the same also went for interrupts. So I didn't need floating point, nor did I need interrupts for my fledgling port. So at the end, we were left with this really tiny set of 12 instructions that just support very basic computing. And we can't really do away with these two, multiplication and division. Those are pretty essential. We could try to emulate them, but that would be really slow. So we'll keep those, and we'll end up with a platform RV32IM. So that's RISC-V. It's 32-bit basic integer instructions and multiplication and division instructions. So this is a very tiny platform to target. And there was one other choice we needed to make, and that is which privilege modes to support. This choice was also really simple because Oberon has no clue about security. There's no security features in Oberon whatsoever. If someone writes malicious software, it can do whatever it wants. It has access to the entire system. So the M mode here, machine mode for simple embedded systems, fits it perfectly. So let's get on to what needs to be done to do the port proper. First, I wanted to set up a build pipeline. I didn't want to open the Oberon system to compile it all the time. That would be really slow, laborious, and difficult to work with. So I set up something called Project Naribo by Peter de Wagter, which runs Oberon programs in a POSIX terminal. And I tweaked scripts a bit and wrote some extra stuff on top of it. And now with a single command, I could build the entire operating system. So that made the process a lot easier to work with. Next up, we'll get into the port proper. This is essentially a simple flowchart detailing how any program gets compiled and put into the Oberon system. So the important parts for our purposes are these two, the compiler and the linking loader. So we have to port the compiler. We have to make it target RISC-V instead of work RISC-V. That's the major task here. And then we also have to work with this linker, which basically takes the compiled source code and then fixes up some references to other dependencies afterwards. So my hope was essentially I could do something like this, just replace the two of them, and then the port would be done. And we'll see how that worked out, I suppose. So let's briefly look at the compiler. I can't go into every single thing I had to do to make the compiler work and run RISC-V, but I'll give you a couple of examples of the sort of problems that showed up. Because it turns out that even though we're moving from one RISC architecture to another, there's still a bunch of problems that can turn up the sort of thing you might not even think about or expect. So the first problem that showed up was with traps. So when a runtime exception occurred, it has to jump to an exception handler and essentially run some code to deal with that, print why it trapped and where it trapped, so the programmer can go in and debug the error. And in work RISC-V, this is one instruction. It's just a jump instruction, which kind of begs the question, how are we sending that information over to the trap handler? Whereas in RISC-V, we have to spend 3 because we also have to put the information somewhere. So I looked at this a bit and investigated in the compiler, and it turns out that in works RISC-V, there are these conspicuous unused bits in the jump instruction going to the exception handler. Half the instruction is completely unused. And the reason for this is, like I mentioned, the architecture is completely custom made. So essentially, he knew he would need this sort of thing. He knew it would be a lot simpler if he left 16 bits completely unspecified and unused. So he just left them there. And essentially, he puts the why it trapped and where it trapped inside those 16 bits. So he saves a lot of space and makes the program more simpler and more efficient that way. Whereas in RISC-V, obviously, it's supposed to be general purpose. It's supposed to be useful for as many applications as possible. So we don't have the luxury of basically not using half the instruction format. So this is one of those areas where work RISC-V being this special purpose makes it a lot simpler for this specific scenario. Another quick example that showed up that caught me off guard and was really difficult to debug, actually, was in something as simple as an if statement. So this example here in Oberon is essentially an if statement saying that if A is not 0, then lots of instructions will run. So the important part to note here is that within this if statement, there's lots and lots of instructions. And I didn't really expect this to be as big of a problem as it was, but when I looked at it, it turned out that, well, in work RISC-V, the offset for how far you can branch is 24 bits. So that's quite many. And in RISC-V, it's only 12. So doing some quick math there, we can see that work RISC-V can branch over 8 megabytes of code. And no programmer worth his salt would ever write that branched over 8 megabytes of code in most circumstances, I think. Whereas RISC-V can only branch over 2 kilobytes. And an if statement containing 2 kilobytes of code is fairly commonly occurring. That happens several times in the system. So this turned out to be a problem where if the branch was too large, the offset would be completely off and some things would jump back and basically cause lots of weird behavior that was really difficult to debug until I actually figured out what was happening. So I won't go into details on the solution. I basically use jumps instead because they have more bits to jump with, so the problem never occurs. But this was made even more complicated by the fact that the compiler is supposed to be simple. So it's only single pass, it does no optimizations or anything. So I don't even know beforehand if the if statement is too large. So I have to work around basically knowing nothing when this problem occurs. The actual point here with these examples is that things that look like they'd be really simple, going from work RISC-V to RISC-V, turned out to be more problematic than I expected. And these are not the only times that occurred. There were several more occasions of this sort of issue occurring. Next up, I'll briefly talk about the linker, or the linking loader, because it both links and loads programs in at the same time, all dynamically in runtime. And the reason I say briefly is because while the compiler took a long time to iron out all the bugs and make it work properly, the linking loader took me about a day, maybe two, to write. Fixing the dependencies is fairly straightforward. Once from one to the other, it's not that different. So this was actually surprisingly easy and a very nice break from debugging a compiler afterwards. So I'll only note one thing, which is that it still gets a lot more complicated because, like I've mentioned several times now, RISC-V is general purpose, work RISC-V isn't. So some of those dependencies we fixing them gets a lot more complicated in RISC-V, and it gets much harder to read. I think the code here speaks for itself more than anything. So, okay, we have the compiler and the linking loader converted from work RISC-V to RISC-V. What about the entire rest of the operating system, like the bootloader and the kernel, the UI, everything? And like I maybe hinted at earlier, it's all written in the Oberon language, which is higher level. So for the most part, I actually didn't have to touch much of this at all. Most of it essentially still worked. I mean, the bootloader is basically just a driver to load stuff from the disk into memory, and that logic is the same across work RISC-V and RISC-V, so I didn't have to change anything. So basically no major changes were needed here. So I'll briefly mention some of the results I found doing this. First of all, I ported this entire compiler, and it is entirely self-compiling. So it can compile itself and then compile other programs. As a result of many different smaller factors, binaries tend to be a bit larger, about 14% bigger than work RISC-V ones. You might have seen some hints as to why that is earlier. Some things take more in RISC-V because it is general purpose. Some programs also take longer to execute. And this is, again, similarly due to it not being general purpose, as some things get more complex. But not by much, and it's not a big performance degradation at all. And some programs actually end up executing faster for various reasons. So finally, I'd like to try and see if this works. I'll try to showcase a quick demo of it running. So this demo will draw a Sierpinski curve when I run this, and then we'll recompile the entire compiler within the system. So that's happening now. You can judge for yourself roughly the speed of this. And then we recompile the Sierpinski curve program, we run it again, and as you can see, it still works just fine. So I'll see if I can get to the next slide. There we go. So finally, what's the point of doing this sort of thing, porting it to RISC-V? Beyond just learning about RISC-V and getting data about RISC-V, which we always need. But the point on a more personal level is that this sort of thing is fun to do. It's fun to work with operating systems and everything from hardware to software. And more than that, it's also very educational to hack on this sort of stuff, to figure it out as you go. I mean, doing this project, I've had to touch everything from RISC-V, emulating RISC-V, the compiler and the linker and everything. So I've had to touch every part of the system while working on this. And as an extension of that, like I mentioned, it's simple. So Oberon is easy to hack on, and I think RISC-V is a pretty good platform for doing that. You learn a lot more doing it on RISC-V than work RISC-V, in my humble opinion, just because RISC-V is a real platform. It's still simple, but it's a real platform, so you'll learn actually valuable stuff about RISC-V doing this sort of thing. But that's only if you can deal, and only if you can deal with the programming language, which to our minds now is fairly antiquated. It was designed in the 80s, and though it's received some revisions, it still feels that way. You get used to it over time, but it's definitely different going from a higher level language to something like Oberon. And finally, there's plenty of stuff you can try to improve while working on Oberon. If you eat your dog food, so to speak, you'll find tons of stuff that really could be improved. And if you try to improve them, you'll probably fall down some rabbit hole figuring it out and learn in the process. And that's quite rewarding. So finally, I'll add some links. I've credited all the FOSS projects I built myself on top of, as well as my advisor, who actually has a talk after me. So I've linked here my port and the emulator, which if you download the emulator, that one also has a pre-compiled image that you can run. And if you run, you can just play with it yourself without having to do much work beforehand. So I based the compiler on a partial implementation by Semmelfalvo, but that one had had quite a few bugs in it, and I had to fix the linker and stuff as well. So, I built it on top of other previous FOSS projects, which I think is quite fitting. So thank you for letting me talk. Are there any questions?
Thank you for talking.
All right,
very interesting.
I'll tell you to stop sharing my screen so that doesn't happen.
There we go. An amazing tunnel effect.
All right, great.
There we go.
Hi.
Cool. No, first of all, awesome talk. Like it a lot. So I have two questions here. One is, are there any fun or unusual applications that comes with Oberon?
What sort of fun and unusual? Like
something you wouldn't see today.
Oh, sure. Let's see. I mean, a lot of the applications that come with it are basically toy applications. So it feels a little bit actually like downloading an operating system from ages ago, where it comes bundled with a toy program that draws Sierpinski and Hilbert curves and stuff like that. That's quite fun. It also comes with stuff you might expect more, just like drawing programs. Actually, a circuit design program comes with it as well, usually, or at least you can download that. That's not something you find bundled with Windows for certain. Those are the ones I can think of off the top of my head, but you can find plenty more if you Google around for it, I'm sure.
Cool. And the other one is, if you happen to have hardware, what do you need to run it on a RISC-V board? Are there any evaluation boards that you would recommend or things like that? Or
right, so that's something I've been thinking about. We haven't gotten it quite working on hardware yet, just because we haven't put in the time. Mostly because I've been busy with other stuff. So currently, it's mostly tested on emulator. It should work on most evaluation boards, but you would have to make a couple of changes unless you manage to set up exactly like Word did with this. Because, for instance, it depends on an SD card and using a PS2 mouse and so on. So if you use a different USB mouse, for example, you might find yourself having to write a USB driver, which I really wouldn't recommend. Personally, anyway. You might find it fun. But...
And then we have a question here from an Amund. Was it difficult to make the emulator work?
I mean, yes and no. I mostly, like I mentioned, like I think the slide mentioned, I borrowed most of the emulator from Ted Fried's emulator at Microcore. So that's an open source, very simple RISC-V emulator. The biggest problem was there were a couple of bugs in that I actually need to raise issues for, that ended up causing issues down the line where, you have the sort of situation where if something is broken in the emulator, it's really hard for you to tell if the issue is in the emulator or the compiler or the program. So that sort of thing ended up being the difficulty more than just the emulator itself. If that makes sense.
You can't trust anything, so to speak. You have to.
Yes, exactly. I couldn't trust anything. So.
Cool. But that's the end of the questions that I can see, unless someone's typing quickly. But I'd like to thank you for a cool talk.
Okay,
much appreciated.
All right. See you around. Good luck with the rest of the conference.
Thank you.